I hope you packed your Dramamine because we're talking about motion. This is the introduction to kinematics, and because we're talking about velocity, speed, acceleration, I hope you packed a helmet because we will deal with several of these things in this introductory video. We're going to find some incredibly important terms that you may want to write down if you don't have them written down already. The first one is going to be displacement. What displacement is? Boom! It is this. Write that down, please. What you need to remember is that displacement is a vector. So much like my favorite evil villain, whose name is Vector, it has both magnitude and direction. So when you express a displacement, you shouldn't just say that something is 15 meters away. You should technically say it's 15 meters to the north, or 15 meters to the southeast, or up or down. Positive or negative should be expressed as well. You should also know the definition of speed. Speed, you should know though, is not a vector. It is a scalar only, so there's no direction with it. But you should be familiar with some values for speed. For example, Usain Bolt, 10 meters per second. Apologies if I misspelled his name. Speed of sound in air might be 340 meters per second, depending on the temperature. And the speed of light, you should definitely get this memorized, is about 3.0 times 10 to the 8th meters per second. There I write it in the proper IB format. An equation that you might see written in your IB data booklet for average speed might look like this, which could mean velocity or speed. They'll have the same looking equation, which can be confusing. Delta S usually in the IB terms means displacement. Now you might think that's kind of delta stupid, which might be fair, but the IB does usually use S for displacement. T is, as you would think, time. Here is an easy problem that I would like you to solve. This final one, why don't you find the average speed in kilometers per hour. So pause it, solve it, now. This part with distance. Drawing a picture usually helps, especially if you're an awesome artist like myself. You will add up just all these values. 4 plus 1 plus 3, I believe, is 8 kilometers. Boom. The displacement is not too tough because you know that his distance now from where he ends up, if this is his start, this is his end, how far is he here? Well, this is 1 kilometer and 1 kilometer. And if you do some trig, you end up with this is square root of 2, and the square root of 2 is about 1.4 kilometers. So to express this displacement, you say that he is 1.4 kilometers northeast. Now for this last one, you want to remember that average speed is not displacement over time. It is the change in distance over time. So we already answered that distance. So that was 8 kilometers divided by 2 hours, and you end up with 4 kilometers per hour. Now, velocity is a slightly more powerful word than speed because it has both magnitude and direction because it is a vector. Not much else to say about that since you already know about speed. Acceleration, however, is your rate of change of your velocity with respect to time. And we usually use the symbol A for that, and that's going to be the equation delta V divided by delta T. The units would be usually something like meters per second squared. I guess you could use something if you were an old school American physicist, something like feet per second squared, which can be said as feet per second, or meters per second, although clearly the metric would be much preferred. To get a little bit more detailed oriented, let's look at an instantaneous versus an average value. So let's say we are talking about 100-meter dash in the Olympics, which Usain Bolt just won. Let's say we've got a graph of his S for displacement versus time. He's going to start at the origin, and he might start with a flat line, and then it's going to go up at a constant rate, like that. Now, if we talk about his average speed, that'd be easy. We would just take the whole 100 meters and divide it by his 9.6 seconds, or whatever that is. But maybe more interesting would be his instantaneous speed, which is at any given instant. So then we could look at his instantaneous speed right when he started, which was 0, because you have to start from rest. Or you could take his instantaneous speed maybe over this time interval, in which it would be pretty much constant throughout the rest of the race and quite high. Instantaneous velocity, exact same thing, except you give a direction to that instantaneous speed. Now the instantaneous acceleration of a 100-meter dash runner would also be interesting, because right here, where he has constant velocity, he would have 0 acceleration, because he's not speeding up or slowing down throughout most of the race. And if you look at his average acceleration over the whole race, that would be very low, because he's only accelerating right here at the beginning. And when he comes out of the starting blocks, he might have a very large acceleration, which is going to cause this curving on the displacement graph. A good friend of mine and yours by the name of Galileo is given credit with coming up with these equations of motion. And these equations of motion, some people try to use them all the time, but they can only be used for very specific things. And it's pretty much stated here, but that is they are only when the acceleration, make a little vector symbol for acceleration, is constant. It can be constantly 0 if you want it to be. You could use these. But usually when we have acceleration, constant value and it has to also be in a constant direction as well to use these equations. Now here it states what all of the variables mean here. Don't forget that S means displacement here, and the U, a little funny, means the initial speed, or often you can think of it as the initial velocity. So these are great equations to have memorized, although they'll always be given in your data booklet. Now, not much to be said about this one for objects falling in a vacuum. The acceleration of these objects, and by vacuum we mean no air resistance, and near Earth's surface have the acceleration that we call g, and g is equal to about, by IB standards, about 9.81 meters per second to the negative squared. Often we can round this in our calculations to 10 meters per second squared. And this is for falling objects, if no air resistance. Here we've got Galileo clearly, because he's holding a pizza and standing on the Leaning Tower. But also, if you have an object that's thrown up, once it's no longer touching your hand, both of these objects have an acceleration of 9.81 towards the center of the Earth.